Honestly, the demo's not that great anyway. It was just a way to break up the monotony of me talking for 30 minutes. So now you just got to deal with me. So this is a talk about fuzzing Soroban contracts. It's going to be technical, though it's not super deep. My name is Brian. I'm an expert in the Rust programming language. I've been working in Rust for 13 years. From 2011 to 2017, I was on the team that made Rust. There's going to be 4 parts to this talk. We probably won't get through all of them. The first talk is about Rust fuzzing generally, just background, no demo. The second part is about the integration of Rust fuzzing with Soroban. No demo. The third part of the talk is going to be kind of the meat of the talk. It's a kind of best practices for fuzzing Soroban contracts, things I've learned in the process of developing this fuzzing support. If we have time, I'll talk a little bit about some of the fuzzing results we've seen, but we might not get there. Okay, so fuzz testing is a very particular type of testing. It's useful to contrast it to unit testing, the most common type of software testing. With unit testing, you write like one very focused piece of code to test another focused piece of code within your program. And it covers, one very specific function. Fuzz testing is significantly different in that you write a testing harness that accepts randomized input bytes. And then these randomized input bytes are fed into your program, and they will test kind of arbitrary paths through the program. And these input bytes are repeated for many, many iterations. So you might run 1 million fuzz tests at a time, all with slightly different inputs. And the goal is that you, with these different inputs, you explore different branches through the program, and hopefully you find branches that you never expected to happen and that indicate bugs. A key feature of fuzzing is that it has a feedback cycle in it. When you fuzz a program, your program is instrumented by the compiler to detect branches that it's running through. And every iteration of the fuzz test, the fuzzer will say, okay, what happened this time when I ran the program? And it will use what happened when it ran the test in order to generate new input for the next iteration of the test. And this type of fuzzing is often called mutation fuzzing. Fuzz testing is a very powerful type of testing. It can find a lot of things that you never thought of, but it's not the ultimately powerful kind of testing. And it's not as powerful as, say, a formal proof, but it can give you a lot of confidence about what your program does. All right, some types of programs are more useful to fuzz than others. Sometimes are more profitable to fuzz or easier to fuzz than others. We generally like to fuzz when our program accepts untrusted input, especially from the internet. And we like to fuzz when there's high security consequences, like financial consequences. Some programs are easy to fuzz, like fuzz tests feed your input randomized bytes. So programs that accept bytes are kind of slam dunks for fuzzing, like parsers, documents. Those are really good fuzzing targets. There's other types of programs where we have sort of, maybe you have multiple representations of the same data type, and you can do conversions back and forth in a round trip between them. Those are really useful for fuzzing. You just generate every possible data type, and then ensure that those types remain the same between the 2 representations. One other type that's really important is when you have multiple implementations. If you have a reference implementation and you're implementing a new implementation of a particular spec, then it's really a slam dunk for fuzzing because you can compare the reference implementation of a randomized input to your implementation. There's cost trade-offs to fuzzing because fuzzing is kind of an unbounded activity. You can fuzz forever and never know when you're done fuzzing. In the Rust world, we do fuzzing with a tool called Cargo Fuzz typically. Cargo Fuzz uses a library called libfuzzer, which is part of the LLVM suite. Rust uses LLVM, so libfuzzer is a good match for it. There's other fuzzers for Rust, many of them under the Rust Fuzz organization on GitHub. Cargo Fuzz is what is usually used and what Soroban supports. All right, here's a demo of basic Rust fuzzing. What I would show you here if I could is that Rust fuzzing is simple, and each Rust fuzz program is its own program. It's not like a unit test where you have many unit tests as part of the same program. When we write a fuzz test, we don't write a main function though. We use a macro called fuzz target imported from libfuzzer. I'm trying to imagine this demo in my head as I'm saying these things. We import a macro called fuzz target from the libfuzzer crate. Fuzz target generates your main function. And it instruments this main function with all kinds of glue necessary to feed that randomized input generation into your test harness. When we run a fuzz program under Cargo Fuzz, you'll see it generates a ton of output. A lot of it is very hard to interpret, but you'll see that it generates many iterations very fast. You'll really quickly get to like 30,000, 40,000 iterations before it finds your bugs, if it finds your bugs. And once it finds a bug, it'll tell you exactly where in your program it failed, and I'll show you a stack trace, and it'll show you the input to your program that failed, and also give you a command to run so you can debug that failing input to your fuzz test. Once you've debugged that bug in your test, you kind of write a unit test, check it into your test suite, and move on with more fuzzing. Okay, next we're going to talk about Soroban. So smart contracts are pretty good targets for fuzzing because they are very high value and they're relatively small. By being small, that means it's really feasible for a fuzz test to find all those nooks and crannies and branches in your fuzz test compared to like a gigantic program where it's very hard to find all the branches in the program. It's feasible to find it's feasible to have very good coverage in test cases for your contracts. And of course, smart contracts have a very high value, so it's worth the effort to do some fuzzing. Really, it's worth the effort to do any kind of testing you can think of for a smart contract. Smart contracts are not as easy to fuzz as things like document parsers, though, because smart contracts don't just accept bytes. Smart contracts tend to be collections of methods. And on this slide, I have an example of like the bare bones of a Soroban contract. We have a data type, here a struct time bound. You can see it's a Soroban type because it's got this Rust attribute contract type on it. Contracts also are composed of methods, here indicated by the Rust attribute contract impl, and we have one method on this contract called deposit. And this method takes Soroban types, address, integers, vectors, and our custom time bound. It's important to note that Soroban has its own type system with a limited set of types, like address, and the Rust layer on top of Soroban kind of encapsulates those Soroban types and Rust types. One thing to notice here about this contract, the deposit method, is that it takes as the first argument inv. And inv is critical in Soroban contracts because you can do nothing in a contract without access to the inv. And that includes things like creating data types. You can't even create an address without an inv. All right, again, these are just some of the types in Soroban. It's got basic types, integers, address, then containers like strings, vecs, and maps. And we're going to run into a lot of complications fuzzing Soroban contracts due to the fact that to construct any of these, we have to have access to Soroban inv. But when we fuzz, the fuzzer only gives us bytes, no inv. Now, again, contracts don't take bytes as input. They take they take Rust types passed to methods. And so what we have to do is we have to create structured input out of those unstructured bytes. And Rust provides us a tool out of the box called the arbitrary trait that converts bytes to any kind of Rust type that implements arbitrary. And so when we fuzz Soroban, we're not going to fuzz with bytes, we're going to fuzz with Rust types. And just on this screen, we got a very succinct example of kind of what happens at the beginning of your fuzz test. This fuzz target macro is the entry point to our fuzz test, and it takes a mouthful of a type called address as Soroban arbitrary : prototype. Exactly what this means I'm not going to go into, but this is a complicated way to name a type that allows us to take bytes from the fuzzer plus the Soroban env and turn them into an actualized address. Like on the screen is a simple example. Address from val takes the input and the env creates an actual address. Okay, now I'm going to do this demo about Soroban. I'm going to do exactly what I did, what you saw me do with the Rust demo. I'm going to do that, but with a real Soroban contract. Now I'm going to imagine in my head what this demo did, and the things to note here are that this is a much more complicated contract. Notice that I'm importing the arbitrary module from the Soroban SDK. Now, the arbitrary module contains all the fuzzing support that's in the SDK, and it's well documented. So the first thing you're going to want to do when you start fuzzing is go read the docs for the arbitrary module. Other things to notice about the Soroban demo are that our input, again, no longer takes bytes. It takes this custom type called input. Now, if you look at our input struct that you can't see on the screen, the input struct derives this trait arbitrary. Again, the arbitrary trait is the standard Rust trait for turning bytes into Rust values. And we have a complicated set of nested structs here that all can be constructed from plain old bytes. And so the fuzz tester will generate many, many combinations of this complicated Rust type in order to feed our contract and fuzz it. Again, there's more complicated named Rust types here that you can't see. I'll just move on from this demo. Okay, because we're not doing demos, this talk is going way faster than I thought. We're gonna have time for Q&A possibly. All right, this next section is about the things that I've learned developing this support for Soroban fuzzing. Hopefully some of this will be useful. The first thing to think about when you're developing a fuzz test is that you really got to think about what it means for a program to fail. And this kind of is going to impact the actual design of your program. Within software, there's all kinds of errors that we expect to happen in the normal course of operation. You encounter input that is incorrect, you return an error. That error is expected. That's not a fuzz testing failure. Your fuzz test is going to generate millions of inputs. Almost all of them are going to generate errors because that's what just happens when you generate random inputs. But you got to be able to distinguish that kind of error, which is expected, from an unexpected error. Unexpected errors happen because the code hits some branch that you didn't actually account for. You didn't write that branch yourself, or you wrote it and you wrote maybe, this is not supposed to happen. And you need to be able to figure out those branches from the expected error branches. In the Rust world, we have a way to do that. Rust provides two error handling mechanisms. It has a normal return-based error handling mechanism called the result type, and it also, where we just return a result of error from our functions. And then it also has a panic mechanism. Panics are unexpected. Panics just blow up the whole world. It unwinds the stack, and that error isn't handled at all. Maybe somewhere up the stack, somebody will catch that panic and do something with it. More often than not, nobody will catch that panic, and the program will just crash. In Soroban, if you panic, the process immediately terminates, and the VM returns an error code saying, the program panicked, I didn't execute this transaction. Now, in the Soroban docs, you'll often see panics as error handling mechanism because it's efficient. It's less efficient to return errors and have them go back up the stack because that just has more bytes in your WASM output. So the docs will indicate just panic, because panic just immediately terminates, no more instructions executed, cheaper to do. This is probably not the way to handle errors in Soroban, though. You don't want to just panic unexpected errors, at least if you're fuzz testing, because your fuzz tester is going to see that something went wrong, I don't know what went wrong, and it's not going to realize that this was a failure or this was expected. The Soroban SDK also, for this purpose, provides another macro called panic with error. It's almost exactly the same thing as panic, except it allows you to specify a return code. So when you write expected errors, a case you accounted for and you expect to see an actual normal execution of your contract, I recommend always using panic with error, because that lets the caller see what actually happened in the error case. And then you can keep using panic as a normal Rust for the unexpected cases. Then your fuzzer, when it calls your contract, it sees, oh, this was a real panic. I'm going to blow up. This was a bug you need to address. In Rust, there's an important caveat here about overflows. You're going to be doing a lot of math in your contracts, and pretty much every math operation you write, you're going to have to think, like, what happens if this operation overflows? Now, by default, if you follow the Soroban docs and you write a math operation that overflows, it's going to panic. And it's going to panic just like that regular unadorned stock panic bang. And you're not going to understand, like, was this a good panic? That's a bad panic. So it's pretty common in Rust code of all types that every single math operation is performed with a special checked operation, and then you explicitly handle what happens in overflows. And I recommend you do this with Soroban contracts. Every single time you write a math operation, think about what's going to happen on overflow, use the checked operation, and then probably what's supposed to happen is the transaction should terminate. So you're going to panic with an error and just terminate the transaction, but in a way that's going to allow your test to realize, oh, this was an overflow error that I actually counted for, that's okay. And that way, if you do that, when you see an overflow that you didn't actually check the code for, you'll be able to realize, oh, this was a math operation that overflowed, and when I wrote that code, I wasn't thinking about it. Maybe that's a bug. Okay, next I suggest there's several viable ways to write fuzz tests. And the one I have found the easiest to think about and get started with is to structure your fuzz tests as a command interpreter. And what I mean by that is that your contract is basically a list of methods that can be called, a list of operations. And in your fuzz test, what I've been doing is I create an enum. Enum is like a union of options, basically. And I create a Rust enum with a variant for every possible method on my contract. And that way, when your fuzzer generates its randomized input, it can generate random combinations of method calls to your contract. So in the demo that I would have run, we had just a vector. The fuzz test would generate a vector of commands. So and a command might be a deposit and a withdrawal. And the fuzz test can say, generate withdrawal, withdrawal, deposit, deposit, withdrawal, withdrawal, and that kind of thing. It's infinite combinations of calls to your methods. And that's a really easy way to get simple coverage across all your methods. So structure your fuzz test as a command interpreter for easy fuzzing of contracts. All right, next thing, Soroban contracts are compiled to WebAssembly, and the Soroban docs will generally lead you to compiling the WebAssembly, then loading that WebAssembly into your tests. But the Soroban SDK also provides a way to compile those contracts to native code, x86 or ARM, for testing purposes. And for fuzzing, you must do this, because fuzzing instruments your code. And fuzzing has a feedback cycle where it looks at what your code is actually doing when it's generating input. And if you compile to WASM and you fuzz that WASM just looks like a black box to the fuzzer. And the fuzzer will literally say, I'm running and running, and I'm not seeing anything happen in your code. And it'll keep generating input, but it will not be all that useful compared to if the fuzzer could actually see what was happening in the code. So whether you're testing a single contract or a whole constellation of contracts, you can compile all those directly to native code. And here's an example of the WASM case. You can see there's this kind of ugly macro contract import bang, importing the WASM, and then registering it in a test case with register contract WASM. Don't do that for testing. I mean, you might want to do that for testing, but for fuzz testing, you don't do that. Native contract, you just use it just like a regular old Rust module. You import your contract, register with register contract. That way your fuzzer is going to see everything that's going on inside all your contracts. All right, finally, this tip is something that's probably obvious to a lot of people, but it took me like 5 months before I realized that Soroban could do this particular thing. So the way you access contracts, call methods on a Soroban contract, is with the client. Here we have a definition of my contract and use of the contract client. This client is generated code. Every time you write that contract impl attribute on your contract, it's going to generate a client for you to call. Because it's generated code, it's kind of hard to see what it's doing. The docs are not very clear about what it's capable of. So it's a little opaque what a contract client does. Basically what a client does is it generates methods for calling methods on the contract. Those methods, do all the serialization and talking to the VM and marshaling the arguments all across the various boundaries. So you can see here we have client.add, and that calls your method. It's the obvious way to call your method. There's also a method called try-add. For every single contract method you have, the client is going to have a try method. If you just call client.add, that any kind of error that happens in the contract is going to panic. Panics are hard to handle. If you call try-add, any error that happens in your contract is going to return a result. And a result has an error in type that can be introspected by your fuzz test. Then your fuzz test can say, was this a good error or was this a bad error? And figure out whether it's supposed to fail or not. I swear I went a long time. I even wrote the entire tutorial without realizing that there's a try-add method here. All right, next tip is about advancing time. When you're testing Soroban contracts, you got to think about the role of time because your test case is going to run all instantaneous, basically. But in the real world, what happens is that you execute a method on your contract, infinite amounts of time go by, then another method calls on your contract, then more time goes by. And you really need to think about simulating this when you're doing your testing of Soroban contracts. There are multiple ways to advance time. The main docs have a very simple way that kind of just frobs the block number and the timestamp. I kind of don't think that's good enough to advance time or to simulate advancing time because if you think about the real world, every transaction you execute, the VM is being instantiated, then destroyed, and instantiated, destroyed, and all that state is being loaded and reloaded. You probably want to simulate that in your test too. This is an example of how to do it. This is also in the fuzzing tutorial. I'm not going to explain it now. I'm almost out of time. All right, finally, one really important thing you can do with fuzz tests in Soroban is you can convert your fuzz tests into what's called a prop test. Now, fuzz tests are awkward to work with. They're standalone executables. They run for an infinite amount of time, so they're hard to put into CI, though some people do. Oftentimes with a fuzz test, you find a bug, the fuzz test seems like it's done working, you throw away the fuzz test forever. But what you can do, and what the Soroban SDK enables, is that you can convert that fuzz test directly into a prop test. A prop test is like a unit test. It can be checked into CI. The only difference between a fuzz test and a prop test is that fuzz tests have that mutation feedback cycle where they're introspecting the program at run. Prop tests can't see what's happening when the program is running. So it generates randomized inputs to feed into your test, but it's not going to actually have the insight into what's going on in the test, and it's not going to generate as high quality input. But good for a regression test when you see your fuzz test. All right, I'm about out of time. Going to skip this. Takeaways, yeah, you heard what I said. I don't need to repeat these all. This is the official fuzz testing tutorial. It covers a lot of what was in this talk and more. I recommend going through it. The examples that I would have run in this demo, link through that tutorial. All right, my name is Brian. This has been Soroban Fuzzing. Thank you very much for coming.
Thanks, Brian. Thanks so much. Yeah, check out that tutorial. It's pretty amazing what comes out of the box with Soroban, how you can use fuzz testing to actually improve the security of your contracts. It's something that not many smart contract platforms enable at this time. It's something that we have from the get-go, and it's thanks to people like Brian and thanks to the pretty amazing design decision and implementation work that's been happening over the past year that we have this.